In this video, we're going to cover section 11.8 on the preparation and reactions of amides. And as we've said previously, amides are some of the least reactive carboxylic acid derivatives. As a result, amides can be prepared from any other carboxylic acid derivative. However, they are most efficiently prepared from acid chlorides. We've seen previously that if we have an acid chloride and we react it with ammonia, in a 2-to-1 ratio, we will form the unsubstituted amide at the nitrogen center. We can also carry out the same reaction with a primary or secondary amine if we wish to have substitution at this nitrogen. Now let's look at some of the reactions of amides. Now, similar to Fischer esterification and the acid-catalyzed hydration of esters to carboxylic acids, amides can also be hydrolyzed to give carboxylic acids in the presence of an aqueous acid. However, this process is quite slow and generally requires heating to high temperatures to occur at a reasonable rate. And so the mechanism for this reaction is exactly the same mechanism that we saw for the hydration of an ester under acid-catalyzed conditions. So again, we require the acid catalyst to improve the electrophilicity of the original amide. Protonating the carbonyl oxygen makes the species more electrophilic, open to nucleophilic attack now by water. And again, we have two subsequent proton transfer steps, which is going to make this less of a good leaving group and this part of the molecule a better leaving group. And so water will pick up a proton from this oxonium to generate the neutral species, and then this nitrogen center will be protonated by the hydronium ion to make this a better leaving group. And so in the loss of the leaving group step, we have reformation of the pi bond. We kick out NH3 ammonia. That leads us to the protonated carboxylic acid. And like we've seen previously, we have a proton transfer to give us our final carboxylic acid. Now this step, I would prefer that water be used because we'll generally have more water present in this reaction than we will have ammonia. So water can be used in this proton transfer to generate the hydronium ion, which is our original acid catalyst. Overall, though, this is a hydrolysis of the amide to give us back a carboxylic acid. Now, similar to esters, amides can also be hydrolyzed to give carboxylic acids in the presence of an aqueous base. Although because this process is slow, we need heat to increase the rate of this reaction. So this is the saponification reaction, but now starting with an amide. So let's take a closer look at this reaction. Now, the mechanistic details for this reaction are directly analogous to the saponification of esters. We start with nucleophilic attack of the hydroxide onto the amide, the carbonyl carbon of the amide, and subsequent breaking of that pi bond. That results in the formation of your tetrahedral oxide intermediate. Now, the loss of the leaving group step, we have reformation of the carbonyl, and we kick out the amide ion, which again is a really poor leaving group because it's such a strong base. But this reaction generally occurs because this amide ion will quickly react with the newly formed carboxylic acid to form the carboxylate. And so it's the formation of this carboxylate ion that really drives this reaction to completion and prevents this process from being reversible, that is, going back to this tetrahedral oxide intermediate. And so similar to saponification of esters, we can stop at the carboxylate, but we normally will proceed with an acid wash if we want to isolate the carboxylic acid. So if you have any questions about the preparation or reactions of amides, by all means, send me an email. Thank you.